Okay. Good morning, everyone. My name is Aaron Johnson, and my team member is Leonard Yu. And today I will be presenting our project for high performance and parallel computing under Team 4, which is parallel big data analytics. So nowadays, organizations generate huge amount of digital data every day. As the amount of data continues to increase, traditional processing methods become slower and less efficient. In this presentation, I will first explain why this problem exists, then introduce two parallel computing technologies, which are OpenMP and MPI. After that, I will present our proposed system and architecture and finally explain our algorithm design using the Foster method before concluding the presentation. So, in the retail, okay, this slide explains why high performance computing or HPC has become important for big data analytics. So in the retail industry, companies generate massive amounts of transaction data every single day. For example, every online purchase, inventory update, and payment record are delivery information is stored digitally. As time passes, these records continue to grow until they become millions or even billions of rows of data. This data is actually very valuable because businesses can use it to calculate the total sales, also understand customer purchasing behavior, predict future demand, detect fraud, and improve inventory management. However, the challenge is that processing such a large amount of data using traditional serial computing takes a long time. A serial program processes one task after another using only one CPU core. The modern CPU computers already have multiple CPU cores, but if only one core is being used, most of the available computing power is wasted. So this is why high performance computing becomes important. And technologies like OpenMP and MPI allow multiple processors or CPU cores to work together at the same time. Instead of processing one record after another, the workload is divided into smaller parts and executed simultaneously. As a result, execution time is reduced significantly and businesses can obtain useful insights much faster. So these are the four major problems using serial processing for big data. The first problem is excessive processing latency. So since every record is processed one by one, analyzing millions of transaction records requires a long execution time. Important operations like daily sales reports or inventory updates cannot be completed quickly. The second problem is hardware resource waste. Today's computers usually have four, even or more CPU cores. However, serial programs only utilize one core, while the remaining cores stay idle. This means the available hardware is not being fully utilized. The third problem is stagnant decision making. So business depend on fast data analysis to make decisions. If the analysis takes several hours instead of a few minutes, managers cannot respond quickly to customer demand. So stock shortage or unusual purchasing behavior will be happens. So the final problem is poor scalability. As the dataset grows from gigabytes to terabytes, the processing time also increases dramatically. Eventually, serial processing becomes too slow to meet business requirements. Therefore, serial computing is no longer suitable for handling today's large-scale data analytics. So to overcome these problems, our project studies two different parallel computing approaches. One is OpenMP and one is MPI. So the first approach is OpenMP. OpenMP works in a shared memory environment. This means all CPU threads share the same memory space inside one computer. The workload can be divided into multiple threads, and each thread processes part of data simultaneously. Since all threads access the same memory, communication between them is very fast and easy to manage. Therefore, one OpenMP is suitable for multi-core computers where the dataset can fit into one machine's memory. The second approach is MPI, which stands for Message Passing Interface. MPI works in a distributed memory environment. Instead of using one computer, multiple computers cooperate together. So each computer stores its own portion of dataset and performs computation independently. After completing the computation, they exchange the information through passing to produce the final result. So MPI is especially useful when the dataset is too long to fit into the memory of a single computer. In simple terms, OpenMP is used for one powerful computer with many CPU cores, while MPI is used when multiple computers work together as a cluster. So the slide illustrates our proposed system architecture. The first stage is data input. The retail transaction dataset is loaded into the system memory. This dataset contains information such as transaction IDs, products, quantities, prices, and purchase records. The second stage is workload partitioning. So instead of processing the entire dataset as one large task, the system divides into several balanced partitions. Each partition contains a portion of the original dataset. The third stage is parallel execution. Multiple processing units or threads work simultaneously on different partitions. Each processing unit independently calculates information such as total sales, purchase frequency, customer behavior, or inventory statistics. Since all threads work at the same time, the total execution time is much shorter than serial processing. Finally, during the aggregation step, all local results are combined into one final result. The design minimizes idle CPU times and reduces unnecessary communications and improves overall system performance. So our algorithm is designed using the Foster method, which contains of four stages. The first stage is partitioning. The dataset is divided into many smaller independent tasks, each task processing a different group of transaction records. This allows many tasks to be executed simultaneously. The second is the second stage is communications. During execution, each processing unit mainly works independently. Only the necessary information is shared between processors. By reducing the communications, we also reduce communication overhead and improve efficiency. The third stage is agglomeration. So instead of creating too many very small tasks, several tasks are grouped together into a larger blocks. So this reduces the thread creation overhead and improves cache utilization. Resulting in this will get a result better performance. So the final stage is mapping. So these larger blocks are assigned to the available CPU cores. The objective is to distribute the workload as evenly as possible so that every processor remains busy throughout the execution. Overall, Foster method helps us to design a balanced and efficient parallel algorithm that makes better use of hardware resources. So now we go through our demonstration part.
Hello, my name is Leonard Lishani. So right now I am going to do the demonstration. So I am going to run one processor with one thread first. This will be our sequential baseline control run. It launches exactly one MPI processors running on a single thread, and the execution time will become our benchmark to calculate all the future speed up and efficiency metrics. So 1.05 seconds is our result. So moving on, I will be running one processor with two threads. So the result is 0.989 seconds. Now I'm going to run with four threads using one processor. 1.045 seconds is the result. Okay, so moving on to the distributed memory scaling. Uh, right now, we do the reverse. We keep the open MP at the one thread, but we scale our MPI processors up to 2 and 4. This will demonstrate the distributed memory parallelism. Now I'm going to run two processors with one thread. The result is 0.964 seconds. Now I'm going to run it with two threads and two processors. This is the result, 0.986 seconds. Now I'm going to run with four threads. The result is 1.5813 seconds. Now I'm going to run using the four processors. For the four processors, I will be running first the only one thread. Four processors with one thread will produce a result of 1.127 seconds. And then I'll be running two threads right now with four processors. The result is 1.21 seconds. Now running four threads. 0.97 seconds. So this is the result for all of the demonstration. I have run a total of 9 commands. One processors will run, no, I mean, the first one is running one processors with three kind of threads, which is one threads and two threads and four threads. And then the two processors will also run one thread, two thread, four thread. Same goes for the four processors. They will also run with one thread, two thread, and four thread. So moving on, I will now be explaining the results. So this is our final result. So the absolute fastest performance happens when we use our two total workers running two separate MPI processors 2 times 1. It finished in 0.964 seconds, giving us our highest speedup of 1.1 and a solid efficiency of 55%. This shows that cutting the data into two completely separate memory chunks works incredibly well. It gives each core its own isolated space to work and avoids the thread syncing overhead that happens when using OpenMP shared threads. And second, we hit a massive bottleneck when we scale up to 8 total workers. The execution time spiked heavily up to 1.58 seconds for the 2 times 4 setup, making it much slower than ever. Our single core baseline. This is a classic hardware limitation because the computer we use only has 6 physical cores. When we threw 8 heavy parallel tests at it, the physical cores got completely jammed and the operating system was forced to constantly pause tasks and swap them out so the thread could get a turn. And this constant context switching created a huge time delay. And finally, the most interesting result is at the 16 total workers, 4 times 4. Even though we heavily overloaded the 6-core CPU with 16 workers, the time actually dropped back down near our record low to 0.971 seconds. And this happened because of a memory shortcut. Splitting the 10 million rows across 4 independent MPI processors shrank the local data chunk size per process down to 2.5 million rows. And at this smaller size, the data chunks fit completely inside the CPU superfast L3 cache memory. And even though the threads were crowded, the processor didn't have to waste time waiting to fetch the data from the slow main RAM, which fully saved our performance. So, the lessons learned from our final project is three things. First is the granularity trade-off. So, over parallelization degrades performance. Balancing the layout between distributed process division and internal thread numbers prevent the core starvation and cache thrashing. Secondly is the synchronization overhead control. Keeping the critical thread region short prevents multi-core locking delays, and utilizing the independent internal thread register before final reduction blocks the maximizes overall system throughput. And for the final one is the data structure optimization. Mapping simple arrays and custom structures using standard types allows the memory blocks to line up cleanly. This optimizes the network packet assembly during collective communication operation. And that's all for us. Thank you.